All right, I'm going to get started. So, yeah, this is kind of the third part of 3 in the class, in the course, I should say. Sort of the first third of the course was about, actually, in some sense, quantum information theory. We talked about like the basics of it and things like, quantum teleportation and the CHSH game and discriminating quantum states. And the second part of the course was about quantum algorithms, Shor, Grover, all that stuff. And we'll now have a segment towards the end of the course about this topic, which is sort of the beginnings of quantum information theory, specifically mixed states and density matrices. So actually today, starting for the first time, I'm going to tell you the full truth, the actual truth of what is a quantum state. It's all been just a partial story so far. Now, it's not like I lied to you about what a quantum state is. And in fact, it's not even that I haven't told you the whole story in some sense. It's just that well, for the sake of mathematical simplicity of, define states in a certain way, and now we'll see the full glorious, full-fledged status of this topic, mixed states. So we talked about mixed states a couple of times briefly in this course. Basically, it's a probability distribution of our quantum states, but now they're going to get sort of central status in our discussion. And we can motivate this a little bit by thinking all the way back to lecture 6. I don't know if you remember that, but that's when we were talking about the rules for partial measurement. If you have more than one qubit and you just measure like one of the qubits, what goes on? And we got into a bit of a mysterious situation where we had the Alice, perhaps standing here on Mars, and Bob standing here perhaps on Jupiter. And we imagined that at some point back when they were together on Earth, they prepared an EPR pair. And that's just 2 qubits in the quantum state, 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. So joint state of 2 qubits, and then Alice takes the first bit to Mars, and then Bob takes the second qubit to Jupiter. And they hang out there. Now, one thing we talked about back then is, suppose we somehow, I promise you that we're never going to hear from Bob again. He's just going to stay on Jupiter. We're never going to go to Jupiter. We'll never talk to him again. Never mind about that guy. So in that sense, Alice just has 1 qubit. It's never going to interact with Bob's qubit again. And she should be able to, we should be able to make a mathematical theory about, her 1 qubit. It should have some kind of state. And, we should be able to make predictions about what measurements she'll see if she just measures her qubit. So we wanted to think about, what we could possibly mean by the state of Alice's qubit. And we're going to try to make sense of that. So one way you could think about it is that, if Bob's just hanging out by himself on Jupiter, for all we know, at some point in the future, he might measure his qubit. Okay, and if he does measure his qubit, then in some sense we really feel we at that point understand Alice's qubit state. If Bob measures his qubit in the standard basis, then Alice's the state will collapse, and Alice's qubit will get into this state. 50% chance or probability of just 0. And 50% chance of 1. And in fact, I think we did some homework about this. You can kind of convince yourself that if you just pretend that this probability distribution over single qubit states is the state of Alice's qubit, then it will indeed explain correctly all the measurements that she could do on her qubit over on Mars. Let me call this thing in quotation marks sigma. Sigma for state, S for state. Okay, but then I showed you something else that might make you feel a little bit weird about this situation, which is, for all we know, Bob might do something else with his qubit and then measure it. In particular, he could rotate it 45 degrees and then measure it. And in particular, if Bob measures in the plus-minus basis, well, what happens? One thing we computed a long time ago is that this state, this 4-dimensional state, sorry, 2-dimensional state that just, sorry, 4-dimensional state, that's represented by this 4-dimensional vector, it's also literally equal to this, 1 over root 2 plus 1 over root 2 minus minus. It's just a simple calculation. And from that, you can see that if Bob measures his qubit in the plus minus basis, then there's a 50% chance that Alice's qubit collapses to plus and a 50% chance that it collapses to minus. So it would seem then that Bob might do this for all we know. And then that would seem to make Alice's state 50% probability on plus, 50% probability on minus. And I'll call this state sigma prime. And somehow that looked kind of worrisome because on the face of it, sigma and sigma prime look, very different. But it seems, Bob can somehow, farther than the speed of light away, cause Alice's state to be either this or this, which looked worrisome. But, the conclusion we saw that meant that it was OK was that actually, in some sense, sigma and sigma prime are the same state. And what does it mean that they're the same state? Well, it simply means that there's no physical experiment you can do that can tell the difference between a single qubit being in state sigma or a single qubit being in state sigma prime. So as we'll see, sigma and sigma prime are the same state. As I said, what I mean here is that no measurements of any sort can distinguish them. OK, and if you have like two physical objects, or a physical object that can be in one of two states, and it's absolutely impossible to tell these two states apart, then you should just call those things the same state. So we're going to sketch an analysis of this fact. And when we do it, we're going to actually come up with a new way to represent quantum states. In particular, a new way to represent quantum mixed states. And it'll be really glorious. It'll be with a matrix. And it'll sort of fix all these little mathematical infelicities and upsetting features that we've seen so far. In particular, the exact same mathematical object will represent this state and this state. So it'll be great. OK, so let's generalize a little bit for our study of these kinds of things. These things are called mixed states, probability distributions, classical probability distributions over quantum states. These happen to be quite simple quantum states, just 0 and 1. But these are, remember, superpositions of 0 and 1. OK, so it's a little bit funny that you have, this classical distribution over these things that have amplitudes, but that's what's going on. So let's think about this question, given some mixed states, whether or not you can distinguish them by measurements. And I'll generalize a little bit. So in general, we'll talk about qubits. So if we have the mixed state of, say, a qubit, and that's just a quantum state with d basic vectors. It looks like this. It might look like, probability p1 of some psi1, probability p2 of some psi2, and some probability pm of some psi m. OK, and of course, these should be non-negative numbers that add up to 1. And these should all be, qubit states. So they should be unit vectors in some d-dimensional space. OK, and these things actually arise all the time. We've actually, so far in the course, always tried to make sure these don't arise, or they arise as little as possible. But in fact, in real life, they arise all the time. If you build some quantum apparatus that produces quantum states, perhaps it's like a machine. Maybe it flips some coins while it's doing so. Or perhaps it involves many qubits, and it involves partial measurements somewhere along the line that we don't necessarily sort of push to the end. Whenever you do partial measurements on some part of a quantum state, the measurement rule induces a probability distribution on quantum states for what happens. And you might not just end the computation or the experiment there. You might go forward and continue to manipulate things that are in a probability distribution of quantum states. So in quantum computing, we always sort of use this principle of deferred measurement to like make sure this measurement sort of only happened at the end, and that the only place we ever got like a probability distribution was right at the very end when we measured. And then we were OK with that. But now we're going to imagine, like, well, what happens if you keep going? I mean, you take a probability distribution of quantum states, put it into some more unitaries, maybe do some more measurements. We want to think about that. Great. So let's say we have exactly this situation. And now let's just find out what happens when we measure it. And instead of talking about, oh, maybe we could do a unitary transformation on it and then measure on the standard basis, instead we'll do the other thing of just imagine measuring it in an arbitrary basis. So remember, for any orthonormal basis, U1 through UD, we can build a measuring device that measures in that basis. OK, so let's say we measure this probabilistic probability distribution over quantum states in the orthonormal basis U1 through UD. OK, so then what is the probability of the measurement device reporting I? OK, for each I being 1 through D, we want to figure out the probability that when we put this into our measuring device, it'll report that it measured UI. OK, well, I claim it's this. It's the sum. J goes from 1 to m of p sub j times UI inner product with psi j squared. OK, and why is that? Well, I mean, just think about it according to the normal rules of probability, right? I mean, with probability pj, this is the probability that the state is psi j, according to this. And then, going way back to lecture 1 or 2 or 3, if you have this being your state and you measure it in this orthonormal basis, the probability that it reports I is equal to the square of the magnitude of the inner product of ui and the state psi j. OK, so that's the probability with which you'll get each of the outcomes I. I mean, this is true for all I going from 1 to d. And now I just want to play with this expression a little bit. In some sense, simplify it. This is probability of getting I, given that the state is psi j. Great. So let's just do a little bit of math trickery. We have here the magnitude squared of a complex number z. Just want to remind you that that's z times z conjugate. It's a fact about complex numbers. And I also want you to think about this as, the inner product between these two vectors. It's like a 1 by d vector times a d by 1 vector. So it's a number, but you could also think of it as a 1 by 1 matrix, according to the laws of matrix multiplication. So in particular, I'm imagining applying this little fact about complex numbers to this thing. And so I would get the complex conjugate of this number. If you think about that as a 1 by 1 matrix, that means that ui psi j star, it's the same thing as the dagger. Right? I mean, dagger is just a complex conjugation and transpose. But if you transpose a 1 by 1 matrix, aka number, nothing happens. But the reason I write it that way is, it tells you, if you dagger, the product of two matrices, you get the product of the daggers in the opposite direction. In other words, this is psi j ui. Okay? I guess possibly I made you do this on like homework 2 or something. Good. So yeah, this expression with the square, which is a little bit annoying, is this times its dagger, which is this times this. And therefore, this is equal to sum j equals 1 to m pj of ui psi j ui. And what's going on here? Really, this is a row vector. This is a column vector. And this is like a column vector times a row vector. So the picture of this internal piece here looks like this. It's a column vector times a row vector. So it's actually a matrix, these two pieces in the middle. It's a d by d matrix. And you see this part, well, first of all, I mean, you also studied on homework 2. This d by d matrix has a meaning, by the way. It's the matrix, so if you think about an operator on d-dimensional vectors, it's the operation of like projecting onto the line defined by this vector. So that's the matrix showing up in the middle here. And also, if you look at this sum, in this piece, ui doesn't depend on j, the sum and. So I can like push this sum and this times pj kind of into the middle here, just by the fact that matrix multiplication distributes over matrix addition. And so we kind of conclude from this little math trickery that this probability of measuring or getting your readout to be I is ui, it's a row vector, times this matrix sum j equals 1 to m pj times this projection matrix times the column vector ui. OK, any questions about this? So this is a matrix. It's some kind of like a convex combination of these matrices. So this is a d by d matrix. Let's call it rho. OK, so in other words, this thing is the row vector ui times the d by d matrix rho times the column vector ui. Good. And so you see, there's a big takeaway from this. The picture here again is, this is ui, this is rho, this is the column vector ui. This all makes like a number, the probability. And there's a huge takeaway out of this, which is that if you're in this mixed state and you want to know like what are all the probabilities with which you'll see various outcomes if you do any kind of measurement, this is like sort of an extremely general measurement measured on any basis. All of these probabilities are entirely determined by this matrix. OK, so I will emphasize that here. Again, this matrix has nothing to do with the basis you measured in. I mean, the basis that you measured in only comes in when you're trying to compute something based on this matrix. So all the outcome probabilities of any measurement only depend on rho. In other words, this one matrix encodes everything you need to know about the state to predict anything about what will happen to this d-dimensional particle. And therefore, we should really just define this matrix to be the state of this the mixed state of this particle. It encodes everything we need to know. And that's what we'll do. So in general, if you have a mixed state like this, you define this matrix rho, which is sum j goes from 1 to m, pj, times this projection matrix, psi j, psi j. And it's called the density matrix for the state. And it's going to be, well, kind of our new mathematical way to write, to define the state of any particle. The word density here is like in the term like a probability density function. That's like that. The definition of a probability distribution is by its probability density function. As we're going to see, this is a lot like a quantum source of probability. but we have a density matrix now. Yep.
So we just use this to describe any state, not even mixed state, like pure state?
Yeah, exactly. So I should emphasize that terminology. If you have like 100% probability on one thing that we used to call a quantum state, and sometimes call a quantum state, that's called a pure state. Okay, and when you have like not 100% probability on a state, like in this case, it's called a mixed state. And this, I'll do some examples, but I mean, this is still all equally true if, it's a pure state, meaning one of the PIs or PJs is 1 and the rest are 0. In that case, you'll have a particularly simple matrix. It's like a rank 1 matrix. It's like matrix, this vector outer product itself. It's the projection matrix onto the line defined by the pure state vector. OK, so let's do some examples. So definitely our first example is going to be this Alice and Bob, Mars and Jupiter situation that sort of puzzled us initially. So example 1. Let's say you have this mixed state. You have a particle, a single qubit, that has a 50% probability of being just a pure state 0 and a 50% probability of being 1. Imagine like a machine that like literally flips a coin, and based on whether it comes up heads or tails, it either gives you a horizontally polarized photon or a vertically polarized photon. And then you could just accept, hey, like I'm going to just accept the fact that like the random polarization state of this photon, is a quantum state that looks like this, a mixed state, and we're going to find its density matrix. So what is it?
Is this distinguishable from the pure state plus?
Pardon me?
Is this distinguishable from the pure state plus?
Yes, definitely. For example, if you have a photon that's in the pure state plus, kind of like a 45-degree rotated photon, and you measure it in the plus-minus basis, there's a 100% chance you'll get plus. Whereas if you measure this in the plus-minus basis, you actually see like no matter whether it turns out to be 0 or 1, you have a 50% chance of measuring plus. So overall, this you'll have a 50% chance of measuring plus. So that's a way to distinguish it.
Why are you measuring plus-minus but not in 0, 1?
That's not a good idea. If you measure in the 0, 1 basis, if you measure this guy in the 0, 1 basis, you'll see 0 or 1 as the measurement outcome with 50% chance each. And also, if you measure like 100% on plus in the 0, 1 basis, you'll also see 0 or 1 with 50% chance each.
Oh, the question was the 100% on plus. OK, sorry.
Yeah. OK, so let's compute the density matrix for this state. Well, it's half. I mean, here's the formula. It's a half. OK, and by the way, of course, this is the vector 1, 0. This is the vector 0, 1. OK, so it's a half times 1, 0, 1, 0, plus a half times 0, 1 times 0, 1. You have to remember how to multiply matrices. So this is a half. This gives you a 2 by 2 matrix. You get 1, 0, 0, 0, plus a half times 0, 0, 0, 1. And so it's this. A half, 0, 0, a half. OK, so right now you might not really know what to make of it, but I'm just telling you this 2 by 2 matrix is going to be our mathematical representation of this mixed quantum state. And I've justified to you that it's actually kind of fine to treat it like that, because using just this information, you can predict the outcome of any measurement that you would ever do to this particle. Yeah?
So this sort of input matrix we're saying, like each row or column afterwards is saying if you're in the first state, the probability of measuring the first one is this scaled?
Not quite. We'll talk about exactly, more clearly how you get the measurements out of this. Well, remember, if you measure in the basis, U1 through UD, I'll bring this up again later. The probability that you see I is this. So if it's the standard basis, you can think about where this is, the 1, 0, 0, and this one is 0, 0, 1. You can think about what this vector, matrix vector multiply looks like. I'll do it shortly. But that's how you get the probabilities. But as we'll see, though, for example, these matrices can contain like negative numbers and stuff. OK, example 2. Well, it's the other one. 50% chance of plus, 50% chance of minus. And remember, this is 1 over root 2, 1 over root 2. And this is 1 over root 2 minus 1 over root 2. OK, so let's compute its density matrix. Well, we got a half. 1 over root 2, 1 over root 2 times the row version plus a half times similar thing with a minus. OK, which is a half, 1, half, 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 plus a half, half, minus a half, minus a half, half. Check me to see if I make a mistake. Finally, we add these two things up, and we get, ta-da, a half, 0, 0, a half. OK, so we get the exact same thing. And I guess that kind of reassures us or tells us that indeed, there's no measurement that you can do, at least of the type that we've described so far, that tells the difference between that 50% state and this one. They'll give the same measurement outcomes for all measurements in any basis. So cool, like how nice that we've got like now one mathematical object that immediately tells us that these seemingly different looking things are actually the same. Or they have all the same behaviors. OK, let's actually do a simpler example now. A pure state example. So let's say you just have a 100% chance. You build a very accurate machine that always perfectly produces the 0 qubit. Well, this also has a density matrix. Okay, well, it's 1 times, of course, it's the column vector 1, 0, times its row version 1, 0. And that's this, 1, 0, 0, 0. OK, get used to it, I guess. This is the sort of like our new version of this state. And but check this out. Let's say we do 100% probability of the pure state negative 0. What's the density matrix for this? Well, it's 1 times, I guess negative 0 is like negative 1, 0, negative 1, 0. And actually, ta-da, that's 1, 0, 0, 0 again. And this is also great. Because remember, like I kind of told you, like, at like lecture 5 or 6, like halfway in, oh, there's this funny thing where like, there's some sense there's no real difference between 0 and like negative 0, or more generally between like any state and like another state you get by multiplying by a complex number of magnitude 1. This is a phrase like the global phase doesn't matter. It was like kind of like a little bit annoying. Like these things look different, but I'm like, well, actually they're the same, because you cannot distinguish them by any measurement. Well, hooray! Like this like annoyance has also been fixed again by this density matrix stuff. Again, happily they have like the same representation mathematically, which is great.
But if I multiply by I.
Let's do that. Example 5. Yeah, if you multiply by I, what happens?
You actually get the negative matrix.
Do you? Well, you get 1 times I, 0. Now what should I write here? I have to write the dagger of this matrix. So it's not just the row version. It's the complex conjugate of the row version. And the complex conjugate of I is negative I. So I put negative I here, 0. And indeed, that fixes things. I times negative I is 1. So we get 1, 0, 0, 0. So hooray. Yeah. So these density matrices are so great. They correct this problem too. So, I mean, I didn't want to introduce too many concepts in this course, which is why we didn't start talking about density matrices on day like 1 or 2 or 3. But I'm so happy we got there now. I mean, hopefully you too will come to love this formalization. Okay.
Some questions. So how's that? Okay.
Go ahead.
It's kind of clear that when you put minus on the 0, then it doesn't change the behavior of the state. But it's not that clear why those two states. I mean, they're different. Like in the real world, if you told me that I'm in this situation or in that situation, like it feels like a different scenario, right? Because at the end of the day, here I know an additional information that the qubit I'm holding is either 0 or 1. Whether in that scenario it's not true.
I would argue that perhaps, like, in some sense, like, you were misled to think there is, like, the independent existence of a state that's, like, 0 and one that's, like, 1. I mean, it was convenient to, like, describe things that way. But, it's like a philosophical point. I mean, if, like, you have a machine that, like, outputs a particle, you have two machines, one that supposedly outputs a particle in this state, and one machine that supposedly outputs a particle in this state, according to some mathematical formalism. And then, like, there's no physical experiment that you can do to distinguish these particles. Then, are they really different? I mean, yeah. Yeah, I mean, actually, I don't know, it's getting philosophical, but, like, some may argue that, like, it's just like, it's kind of cheating you by saying that, well, it's hard to say. I mean, it depends on how you look at it. Yeah, some might say that actually this state is indeed different from this state. It's just, that this 50% probability is like reflecting your like classical lack of knowledge about the true state of the qubit. And some people feel that like the true state of a qubit is indeed just like a vector. And then you can put this probability on top of it to like sort of model the uncertainty about it. And that's how we model the world. I guess other people, and like maybe I like this viewpoint, are just like, nope, like I'm just granting full-fledged status to like probability distributions in my reality. And then, I'm like, it's not like this. Like, this is not how you describe that photon. It's just like, this is how you describe that photon. Yep.
Do you think that with the CHSH game, there might be some experiment that you could do which would prove that it's definitively one or the other?
I mean, no. I mean, according to like the laws of quantum mechanics that have been accepted, since the 20s, yeah, no, these are like mathematical. These are, yeah, there's no way to distinguish this from this. I mean, it's a little bit fishy because like, you might ask, like, how do you get into this state? I mean, did you like flip a coin, like a classical coin? And then you can say like, what is randomness and all sorts of things. I mean, like the more natural way you get into the state is by like, well, measuring like one particle in like a two qubit entangled state. And yeah, so whether you just view this as like a convenient mathematical formalism of like some underlying truth about like, I don't know, vectors, or you just take this to be the truth, I guess it's up to you. Yeah?
So would there be an issue with this formalism if like Alice and Bob were to meet up later in the future and whoever does the first measurement, like say Bob does the first measurement, and Alice doesn't, so Alice would right now have like that mixed state.
Yeah.
And then Bob says like, I did XYZ operations and then got this readout. Then won't that change?
Yeah, good question. So a couple of things. One, if it's possible that in the future Alice and Bob are going to get together and make their particles interact, then you actually better remember that these particles have a joint state. And the only way you'll be able to like predict the experiments involving their two particles together is by using their joint state. That said, even that joint state, like we're now going to view as, it's now going to be like a 4x4 matrix. But the good thing, and I mean, I haven't formally proved this, but I've like mostly sketched this, is that on the other hand, if Bob and Alice are going to be completely separate forever, then there's no, like, so say they start with this EPR pair, and then we say, oh, like in isolation, Alice's particle is in this state, aka this state. you can mathematically prove, and it's sort of been sketched over the lecture, is that there's no local operation Bob can do to his qubit that will change the mixed state or density matrix of Alice's particle. He can change their joint state, but this just represents the state of Alice's particle.
I see. So these are equal, assuming that they'll never like actually exchange information.
Well,
Because if they
these two states as they are just considered to be equal. But it could be that a particle that itself has this state when viewed in isolation is also entangled with another particle. And then the joint state of those particles is not sort of merely defined by Alice's state and Bob's state. In just the same way, essentially, that, let's say you build a machine that tapes two coins together so that they'll always land the same way and flips them, and then nobody looks at them yet, but you separate them and give one to Alice on Mars and one to Bob on the moon. On one hand, it's correct to say that the state of Alice's coin is 50% heads, 50% tails. And it's also correct to say that the state of Bob's coin is 50% heads, 50% tails. And if Alice and Bob are never going to talk again, and you're only going to start building an experiment that does something based on whether Alice's coin is heads or tails, then it's fine to just say OK, Alice's coin is in the state 50% heads, 50% tails. That's it. Everything going forward will be fine. And Bob can turn his coin over or look at it, and that doesn't affect things. But if you're ever going to bring the two coins back together and build a machine that looks at the joint outcome of the two coins and does something based on that, then you better remember that they started out correlated, either both heads or both tails. So it's really the same thing here. I mean, this is the, in isolation, state of Alice's qubit. It's also the state of Bob's qubit. I mean, it's symmetric. And yeah, if they're never going to talk again, then it's fine to just treat this as the state of Alice's particle. But this is good to actually do. But if you're going to treat them together again, you should remember that they're actually in this joint state. I don't know what example number I'm on. It's an EPR pair.
Example 6.
Thanks. 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. So just to get the terminology clear, this is a pure state. You can think of it as a 4-dimensional qubit, too, if you like. It's this vector. But now we would like to make everything a density matrix. So this has density matrix. That's 1 over 1 times 1 over root 2, 0, 0, 1 over root 2. 1 over root 2, 0, 0, 1 over root 2. Okay, which is, let's see if I can do this, half, 0, 0, a half, 0, 0, 0, 0, 0, 0, 0, 0, half, 0, 0, a half. So this is the joint state of these two particles. And there are some rules that we'll eventually get to, things called partial trace, that tells you if this is the joint state, how you can produce that this is the state of Alice's qubit, and it's also the state of Bob's qubit. Yeah. OK, I was going to do some more examples, but I don't want to run out of time. Let me just say a few things. So far, in the examples we saw, the number of different pure states was at most the dimension of the vectors we were talking about, but that's not necessary. You could have a probability distribution over 35 different, 2-dimensional qubit states, and it would have a 2x2 density matrix.
It doesn't have to be finite?
No, it doesn't even have to be finite. Although, I guess we'll see. As you see, for each density matrix, there's more than one way of realizing it like this.
Yeah.
More than one way to what?
Realize it as a convex combination of pure states. And I guess there's, I think, correct me if I'm wrong, there's always one where it has a finite support.
Is that right?
Or maybe not.
What? This matrix could be realized as this and that? Is that what you mean?
The question was like, for a fixed density matrix, can it always be realized as like a probabilistic combination over like finitely many pure states?
It's finite dimensional.
Yeah, if it's finite dimensional, yeah. I think so, yeah. Yeah.
But it's not unique, right? Because
It's not unique, yeah. I'll talk about all this, but this is also a good point. And I was also going to do like a long example with a Q trit, but I'll just skip the details and tell you this one, this fact. Okay, here's an example. You can do a Q trit example. If you have a 50% probability of 1, which to remind you is 1, 0, 0, and 50% probability of, I just made this up, 1/3 times 1 plus 2/3 times 2 plus 2/3 I times 3. These amplitude magnitude squares do add up to 1. The density matrix is, and you have to remember when you do the column to row conversion, you have to take the complex conjugate. But long story short, it turns out to be this thing, which I'll put up just to have like an example of a slightly bigger one. 5/9, 1/9, negative I/9, 1/9, 2/9, negative 2/9 I over 9, 2/9 I, 2/9. Okay? That's an example of a 3×3 density matrix that corresponds to this mixed state.
It's like the diagonals always add up to 1.
Oh, very good. Yes, the diagonals are going to always add up to 1. That's a good. We're going to see several key properties of density matrices, and that's one of the properties.
It's because of the probability of outcomes in standard basis, right?
Yes. So we'll exactly compute those, and thereby deduce that fact. You guys are very good. You're fast. I'm going to do it fast. OK, so say we measure any mixed state in the standard basis, which is, like U1, which is 1, which is 1, 0, dot, 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 0. U2, which is 2. This is for a qubit, which looks like 0, 1, 0, dot, 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 0, etc. Well, the probability that you read out 1, if you remember the rules, right, it's like U1, the row version, times row times U1, okay, which looks like this, 1, 0, dot, dot, 0, times row, times 1, 0, dot, 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 0. And what if you do this vector matrix vector multiplication? Let this matrix times this vector. This one just picks out the first column, and then this just picks out the first row. So you get the number row 1, 1. Okay, so given any density matrix, if you measure on the standard basis, the probability that the readout is 1 is the top left entry. That's 5/9 here. And perhaps you can see, since you're pretty quick, that the probability that you'll read out I for a general I between 1 and D, well, it'll look like this, except the 1 will be in the ith position. Some 1 here in the ith position. OK, and that 1 will pick out like the ith column, and this 1 will pick out the ith row. So you'll get row II. OK, so this is, well, I won't rewrite it here, but in the interest of time, but this is basically like a fact. If you take any qubit state, which has this kind of density matrix, and then measure on the standard basis, the probability of seeing each of the possible outcomes, 1, 2, 3, up to D, are the diagonal entries. In particular, that indirectly proves that the diagonal entries of a density matrix will always be non-negative numbers that add up to 1. Good. OK. So now we can talk about, let's indeed talk about properties of density matrices. And I'll actually give you like a short criterion for like when a general matrix is a density matrix. So So first of all, we'll list some properties that these things have. Well, first of all, I'll call it rho. If you have some d by d matrix rho, they're symmetric. Well, as always, due to the annoyance of complex numbers, we shouldn't write symmetric. We should write Hermitian. That's the complex numbers analog of symmetric. It just means the dagger of the matrix is itself. OK, so if you like to forget about complex numbers, then it just means they're symmetric matrices. Otherwise, you should remember that like when you do the transpose, you have to negate, or you have to conjugate the complex numbers. OK, so this is an example of a Hermitian matrix. And why is that true? Well, just remember, these rows look like sum over j of pj times, psi j. And what would happen if you daggered this thing? Well, I mean, you played with all the properties of dagger transpose a long time ago. It doesn't affect this number, and then the dagger of this is itself. Okay, so that's why they're Hermitian. OK, another property is that they're positive. But I use that in the matrix sense. The meaning of a matrix being positive, aka positive semi-definite, this is some linear algebra talk, is for all unit vectors u, dagger, rho, u is a non-negative number. OK, this is the definition of a matrix rho being positive or positive semi-definite. Actually, usually when you look it up in a book, they just say for all vectors. But it's easily seen to be equivalent to the statement for all unit vectors. Because scaling this by a scalar doesn't really change things. It'll get canceled out. OK, so why is this fact true? Well, one easy way to see it is if you have any unit vector u, you can just extend it to an orthonormal basis of CD. And then you could say, oh, perhaps I would measure rho in that basis. And then this quantity, by definition, would be the probability of the measurement device outputting u. So it would have to be a non-negative number. Or you can easily check it from this as well.
Why is that useful for us?
Well, it's just a fact about, these are facts about density matrices. And I'm going to write down one more fact, and then I'll say like these three properties actually characterize density matrices. So you'll be able to easily recognize whether a matrix is a density matrix for some mixed state or not. Also, there'll be another little punchline too when I finish writing them down. And the third property, I also want to call this like the 0th property, the first property, and the second property, is this, just sum of these diagonal entries equals 1. Right, because this is these are the probabilities. You'll measure each outcome in the standard basis. Of course, they have to add up to 1. And if you're a lover of linear algebra, you may recognize this as the so-called trace of rho, sometimes denoted trace rho. So if you start reading quantum books, they'll talk about trace all the time, and it means this number. Great. So I've convinced you that density matrices satisfy properties 0, 1, and 2. Let me just assure you, and we'll indirectly see this as we go along, the converse is also true. I guess we'll see this as we go along. Namely, that any matrix that satisfies these properties is the density matrix for some mixed state. First, I'll just make a definition. D outcome or d-dimensional density matrix is a matrix rho in a d by d matrix of complex numbers with well, I should add Hermitian matrix here, with rho greater than or equal to 0. That's somehow, this positive condition is somehow times written like this. Some people like to do it with squiggly things, but we'll just write it like this. And property 2, sum I equals 1 to d of rho ii equals 1. Okay. Now, actually, having said this, I want to just draw your attention to a similar definition that might be made in a sophomore class, math class, a probability class, where you might define, a d outcome probability distribution, or a probability distribution with sample space 1 through d, is a vector that's non-negative and its entries add up to 1. It's almost the same thing, right? Except you put a little curly tail on the p and turn it into a row. And instead of a vector, it's like a Hermitian matrix. But this is somehow not a coincidence. We're going to talk about this in upcoming lectures. But quantum states, mixed quantum states, are like a strict generalization. They're like a quantum random source. They're like a strict generalization of a classical random source, a classical probability distribution. So in fact, everything that we're going to do over the next few lectures is just taking probability distribution, probability theory, like you learn as sophomore. And everywhere that the word vector appears, if you cross it out and write Hermitian matrix, then you get quantum probability theory, which is the sort of statistics and probability of mixed states. So we'll pursue this analogy quite a bit in the future. OK, so right, so now we could, I've just given this to you, but let's imagine that you've digested it and have come to accept it. And you might say, okay, now I'll just work with mixed states or density matrices throughout my quantum doings. Great, you can do that. And even some people present quantum computation that way. We didn't, to keep it a bit simpler. But we should now go back and look at the basic things that we do with quantum states and redo them a little bit in this density matrix formulation. Luckily, there's only two things we really do with quantum states, which is apply unitary transformations and measure. So let's just check what happens there. So let's say you have now a quantum mixed state, which is, it's like, pi probability of psi I, for I equals 1 to m. Okay, let's say you, did some quantum experiment or quantum computer, and it got you into this state, these various mixed states, probabilities of these various pure states. Well, on one hand, we now know it has a density matrix, rho, which is given by sum, j goes from 1 to m. I guess I'll call it j's. Pj, psi j. OK, but one thing that we always like to do with them is apply unitaries. So let's say we apply a unitary u. Again, let's imagine these. Again, this quantum state is like a qubit state, so it's d-dimensional. So this u is like a d by d unitary matrix. And I just want to work out what is the density matrix of what results. So we'll just work it out in the natural way. Well, the new mixed state, well, would of course be, for each j, a pj probability of u times psi j. This is j goes from 1 to m. Okay, that's of course what would result if you just took whatever this was and applied u. And now let's compute the density matrix for this. We'll call it rho prime. Well, it's sum j goes from 1 to m of pj, and then u psi j times the dagger of u psi j. And what happens when you dagger this? Let me just cross it out here. You'll get psi j times u dagger, right? And then I'm going to do this trick again. U does not depend on j, so I'll push this sum and this pj to the inside. And what I'll get is u, and then on the inside I'll get sum over j, pj, psi j, bra, and that'll be rho. So I'll actually get u, rho, u, dagger. And that's it. So it's just like a new thing to remember. Like in the old world, when you only had pure states, if you were in some pure state psi, and then you did a unitary transformation, that's like the main transformation you can do in quantum, like the new pure state was u times psi. And now it's just a little bit different. If you have some generic state, a mixed state, and it had density matrix rho, and you apply a unitary transformation u to it, the density matrix of what results is u, rho, u, dagger. Okay, and the math nerds would call this conjugating rho by the unitary matrix u. Okay, it's really, I mean, these are all operators, right? And this is like a natural operation. Rho is like some action. It's a matrix, so it's like some action on d-dimensional vectors. And this is like, oh, first like rotate space by u, then do the action, then rotate space back by u. So it's kind of like saying, oh, do the same action, but just like in a twisted view of space. Okay. So that's what happens if you apply a conjugation or apply a unitary transformation. And then the other main thing that we do in life is measure quantum states. And I only want to talk about measuring in the standard basis because, as we've seen before, I mean, although you can measure in a general basis, you can simulate that by a combination of unitaries and measuring in the standard basis. So you might think, like, what is there to say? We already know what happens when you measure in the standard basis, right? Like the probability of seeing each outcome or each measurement outcome is given by the diagonal entries in the matrix. But I kind of want to slightly blow your mind here. Because when you measure, right, you get a random outcome. So like the new, it collapses the state in some sense. You get like a new situation where you see either, ket 1, ket 2 up to ket d, each with various probabilities. And so to describe the situation after you measure, you can have a mixed state, right? I mean, that's what a mixed state is, like a probability distribution over different pure states. So actually, measurement takes you from a mixed state to another mixed state. It's kind of like, if you don't just look at the outcome, but just merely model the fact that like after you measure this particle, it'll be in one of various states with various probabilities. That's just a new mixed state. So indeed, if we have some mixed state with density matrix rho, and then let's say we measure it in the standard basis, then, we actually worked it out somewhere. You get into like a new mixed state where you have like a rho 1, 1 probability of collapsing to 1, and a rho 2, 2 probability collapsing to 2, down to a rho d, d probability collapsing to d. And this mixed state has a density matrix. And what is it? Well, it's like rho 1, 1. OK, and then 1 is this vector. And then we put its rho version. Plus, the last one is rho dd. That's this vector. This is ket d here. 0, dot, 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 0, 1. We put its horizontal version. OK, and what is this vector product? You'll get a 1 in the top left corner and zeros elsewhere. And then, well, I'll just do the last one. Here you'll get like this vector product. You'll get like a 1 in the bottom right corner and zeros elsewhere. And in general, like the 2 case, you'll get like a 1 in the 2, 2 position and zeros elsewhere. So you'll get this matrix. The matrix gotten by zeroing out all the stuff that's not on the diagonal. So the conclusion is this. The operation of measurement takes one mixed state to another, one density matrix to another, and it has the effect of just zeroing out all the non-diagonal entries. Yeah?
Does this mean that two mixed states are equivalent if and only if they have the same diagonal entries?
No. The question was whether this means two mixed states are equivalent if and only if they have the same diagonal entries. Two mixed states that have the same diagonal entries will have all the same measurement probabilities if you only measure them in the standard basis. But they can potentially be distinguished them by measuring in other bases, or alternatively, doing a unitary transformation to them and then measuring. In fact, exactly the scenario that we talked about before, 50%, 0, 50%, 1. We talked about this exact thing. Has this density matrix. And 100% plus has this density matrix. So they have the same diagonal. And indeed, if you measure them in the standard basis, you will get the same measurement outcomes. You won't tell the difference between this and this. You'll see each the two possibilities with probably a half each. But there is a way to distinguish them, measuring in the plus-minus basis. Or first, doing a certain unitary transformation, and that'll change the diagonals. Cool. Any questions about this? This always, still to this day, makes me think a little bit. It's a little bit funny. Yeah?
Do you get some similar looking beautiful result if you measure the first two qubits and then look at the next segment?
Yeah, it depends on your aesthetics if you call it beautiful. I always there's a rule for that. I mean, it's called doing a partial trace. And it's sort of the mathematical rule that's used if you have a multi-qubit state to figure out the state of some subset of the qubits. Just like when Alice and Bob shared an EPR pair, they had 2 bits, and we were like, well, what's the mixed state of just Alice's bits by itself? That's kind of like this sort of partial measurement, or it's like a partial version of this. And it has a complicated looking formula, but it's arguably simple. Actually, well, we'll get to it later. Yeah. So it depends on your aesthetics whether you think it's beautiful or not. This one's nice, though. What I also like about, I'll say, all this density matrix stuff, I mean, I love this stuff, is that, in the old world, we had this 2 very different operations. There's unitaries, that was one one simple thing, and then measurements, totally different thing, sort of different rules applying to them. Now it's looking a little less crazy, applying a unitary involves, doing this to your row. Measuring involves, doing this to your row. In fact, we're going to define a more general notion called quantum channel, which just incorporates in a natural way both applying unitaries and measurements. And it really tells you genuinely every way in which a mixed state can transform. So you can look forward to that. OK, so good. We must press on. Now we're going to have a little linear algebra interlude. It seems like, how is this an interlude? We've been doing so much linear algebra, but we're going to really hit the linear algebra now. It's going to be like a peon to this glorious object, a Hermitian matrix. Such a great kind of matrix. I love Hermitian matrices or symmetric matrices. I don't want to say every other kind of matrix sucks, because there's unitary matrices. Those are also nice. And they're not necessarily Hermitian, right? Unitary matrices are not necessarily symmetric or Hermitian. But man, Hermitian matrices are so great. And I'll tell you why. So d by d, I really want to write symmetric here. But again, because of the complex numbers, I have to write Hermitian. Oops. Matrices M are so great. I'm writing it here. And what makes them great, and why do we love them? Well, the math talk version of it is they're great because they have real eigenvalues. And they have d real eigenvalues, and the associated eigenvectors, or they have associated eigenvectors which are orthonormal. And that's great. That's the math talk, orthonormal basis of eigenvectors with associated eigenvalues that are real. So joyful. In the real talk version, I'll say it like this. This is a simple linear algebra fact that I'm not going to prove it, but maybe you saw it in your linear algebra course. For any Hermitian matrix M, there's an orthonormal basis of space. We'll call it V1 through Vd of CD. And real, I'll call them stretch factors. Real term is eigenvalue. Lambda 1 through lambda d, possibly positive or negative, such that when you ask yourself, hey, M is like, it's a linear transformation. It's like an operation on d-dimensional vectors. Like, what operation is it? M's action is, it's this, scale or stretch by factor lambda I in the vi direction. I mean, simultaneously for all I. Okay? So if you have any Hermitian matrix, this is how you think of a Hermitian matrix. You got a Hermitian matrix. It just means there's like some orthonormal basis, not necessarily the standard one, though some. Plus, some like real number associated to each of the directions, such that its action is like stretching by that real number in the associated direction. Okay, if it's negative, right, that's like a reflection. Okay, so that's a Hermitian matrix. It's just like generally a scaling operation, but like in a rotated basis. Great. And by the way, once you have this set up, the matrix itself, M, is the sum, j goes from 1 to d, of lambda j times this projection. Right, if you remember your linear algebra, this operation is projection onto the vector vj. Okay, and this is like stretching. And yeah, so you actually kind of studied this, I think, in homework 2. Yeah.
Does that mean that then our probabilities are eigenvalues and our standard basis are the eigenvectors of our matrix, our density matrix?
Yeah, we're going to get into that. But basically, if you have in case I run out of time, density matrix is a Hermitian matrix. And the punchline that we'll see is, so therefore it has, in particular, some orthonormal basis plus these stretch factors. The punchline is that these stretch factors are going to be non-negative numbers that add up to 1. And so then you can almost think of it as like, alternatively think of it as like a probability distribution on this orthonormal basis. So we'll get to that. Actually, I have to now say like one annoyance, which is important to raise, which is that I do not say the word unique here. I don't want to say most of the time it's unique, but kind of most of the time it's unique. If the lambdas are distinct, then the basis vectors are the basis is unique, but not always. Like imagine like you had like a 3x3 Hermitian, so it has this like orthonormal basis, and the stretch factors are like 5, 5, and I don't know, -2. But in particular, these two both have stretch factor 5. Then as an action, right, what it's really doing is it's stretching everything in the plane given by these two vectors by 5. So it's like a 5 dilation in this plane and like a -2 or whatever stretch in this direction. And so it's actually not really too natural to pick out a particular basis of this plane, right? Like if I picked out any basis for this plane and said, oh, it's stretching by 5 in these two directions, it would be the same thing. So the real interpretation is actually like, you should just think of like that guy is like stretching by 5 in this plane and like by -2 in this direction. Okay, but when the stretch factors are distinct, then like you get uniquely defined like basis. That thing I just said is not too important. Okay. Good. So like I was just saying, density matrices are Hermitian matrices. They're Hermitian matrices with 2 extra properties. They're positive, aka positive semi-definite, and their diagonal entries add up to 1. So let's just work out what that implies. about these eigenvectors and eigenvalues, or basis and stretch factors, if you will. OK, so a density matrix rho has these orthonormal basis. An orthonormal basis and stretch factors lambda 1 or eigenvalues lambda d. Now, but it has two other properties, right? So it's also positive. Written like this. Which means that, the definition of that is that for all unit u rho u is greater than or equal to 0. In particular, like what if you plug in u to be some bi? Right, well, like rho stretches vi by lambda I, and then you basically get vi times lambda I vi. Because rho stretches by lambda I in the vi direction. OK, and vi interproduct with vi is 1 because it's a unit vector, so you just get lambda out, lambda I out. And what that proves is that for a density matrix, all these eigenvalues, these stretch factors, have to be non-negative, which is half of what I told you the punchline would be. OK, and now for the other punchline. OK, so this density matrix has these v's, this orthonormal basis associated to it by virtue of it being a Hermitian matrix. So also, it has these v's, so there exists a unitary u which moves or rotates v1 through vd to the standard basis. 1 through d. And so say we apply that. To rho. OK, well, that transforms it into rho prime, which is u rho u dagger. So on one hand, rho prime has the same stretch factors as rho. Why is that? Well, look at rho prime as an action. Like it rotates space, then does like a stretch in a certain basis, and then rotates space again. The rotations don't really matter. It's still like the composite effect here is still like some various stretches in some orthonormal basis. So this doesn't change the eigenvalues. Okay? Rho prime still has the same lambda i's. But on the other hand, the point of doing this is to like change, rho to a mixed state where it's like a probabilistic ensemble where all the vectors in the ensemble are just the standard basis vectors. And what that means is like rho prime is a diagonal matrix. But the stretch factors of a diagonal matrix are just the entries on the diagonal. So that means that the eigenvalues, the lambda i's for rho prime, which are the same as those for rho, are just the diagonal entries of rho prime. So the lambda i's are the diagonal entries of rho prime. And rho prime is a density matrix, so they add up to 1. OK, which is a short proof that there's another property of these eigenvalues of a density matrix rho. They add up to 1. OK, so just to summarize and conclude here. A Hermitian matrix rho, that's a density matrix, has its eigenvalues non-negative and adding to 1. And in fact, this is if and only if. If you have a Hermitian matrix that has non-negative eigenvalues adding up to 1, they are a density matrix. It's not hard to show that. And so in particular, they form a probability distribution, which is kind of interesting. And therefore, a probability distribution over what? Well, I mean, you can think of them as a probability distribution over the V's. So as a consequence, any density matrix rho, now let me write in small letters here for a second with distinct eigenvalues, has a canonical mixed state associated to it. And that's the one that's like, you know, probability lambda I of vi for I ranging from 1 to d. So given any density matrix, it's a Hermitian matrix. Therefore, you can think of it as, you know, there's an orthonormal basis of v's, and rho's action is to like stretch in that orthonormal basis by various amounts. By virtue of being a density matrix, these stretch factors will be non-negative and they'll add up to 1. And so this is like a sensible mixed state. You know, for each I going from 1 to d, you can say probability lambda I of this unit vector. And like the density matrix of this mixed state will be rho. And one thing that sort of shows is that like if you have a mixed state in dimension 5, but you have like, you know, 1,000 different probabilities, like probability p1 of this state, p2 of this state, up to probability p1000 of this other 5-dimensional vector, it's equivalent to a mixed state that has exactly 5 different pure states. And not only that, but like these 5 pure states are orthonormal. So it's kind of like a more canonical version of a mixed state. Let me mostly conclude by like talking about this footnote. So I said before, if some of these lambdas are the same, then this is not really canonical. Like, you know, you might have a subspace that gets stretched, where both vectors get stretched by the same amount. It's not so canonical to pick out one basis. It's more like this subspace gets stretched by a certain amount. OK, so in that case, it's like not always like fully canonical, but that's OK. But I don't want to totally, you know, tell you to forget about this and don't worry about it, because actually there's one important density matrix where this like doesn't happen. In fact, it fails to happen in like the most blatant way. It's the density matrix where all the eigenvalues are the same. And I'll mostly close by telling you about that. There's an object called the maximally mixed state. In d dimensions, or for qubits. It's the mixed state with density matrix, basically the identity matrix, but times 1 over d. 1 over d times the identity matrix, which is this matrix. OK. This is a symmetric matrix, a Hermitian matrix. You know, its action is to just scale everything by 1 over d. It's scaled by 1 over d in every direction. So it's positive matrix. You know, it only scales things positively. Its diagonal adds up to 1, so it's a density matrix, et cetera, et cetera. It has all these properties. Yeah, so it stretches by 1 over d in all dimensions, directions. Its eigenvalues, all its eigenvalues are 1 over d. And there's no really canonical basis. I mean, every basis is kind of the same. And in fact, our original example corresponds to exactly this case. Remember, this Alice, Bob, Mars, Jupiter thing had density matrix exactly this, 1/2, 0, 0, 1/2. This is the maximally mixed state in 2 dimensions for a qubit. Indeed, as we saw, you know, you could treat it as, you know, a 1/2 probability of 0 and a 1/2 probability of, OK, ket 1. This is an orthonormal basis, 0, 1, and you stretch by a half in both ways. It was also equivalently a half probability of plus, half probability of minus. In fact, for any two orthogonal qubit states, it's the same as 50% chance of this one, 50% chance of that one. Let me just end by saying this maximally mixed state is, it is the quantum probability as the uniform probability distribution is in classical probability. This is the kind of the most random quantum state, and therefore it plays also an important role in quantum probability. So yeah, when we see each other again next time, we're going to really start to pursue this generalization, quantum probability of classical probability, and learn more about quantum channels and other such things. And this is a topic that I think is really nice because it illustrates there's more to quantum computing than just like algorithms. We've talked about quantum algorithms, and there's Shor and there's Grover, but this quantum probability stuff is very interesting, and we'll get into quantum communication and information theory and learning and things like that. And there's lots more to do just besides looking for quantum computing algorithms. Okay, so see you in a week.